There are lots of fun things you can show with Cauchy-Schwarz, but most of the time you'll be using it to establish an upper bound, one typically involving a magic letter named epsilon. But for practice, here are some fun applications. For any angle theta, the absolute value of cosine squared theta minus sine squared theta is less than or equal to 1. Proof. Apply the Cauchy-Schwarz inequality to x equals cosine theta sine theta and y equals cosine theta minus sine theta. X dot y is equal to cosine theta plus sine theta minus sine theta, or cosine squared theta minus sine squared theta. Also, the norm of x times norm of y equals the square root of cosine squared theta plus sine squared theta times the square root of cosine squared theta plus the square of minus sine theta, which is just 1. Cauchy-Schwarz immediately tells us that the absolute value of cosine squared theta minus sine squared theta is less than or equal to 1. Note that we could have proved this theorem without applying Cauchy-Schwarz. In case you forgot, the left-hand side is just the double angle formula for cosine. You use this equation tons of times when integrating cosine squared theta. The next example is a famous one that translates to: the square of the average is less than or equal to the average of the squares. If you're not sure what this means, it's always good to write down an example. For the numbers 1, 2, 5, 6 and 10, the square of the average of 1, 2, 5, 6 and 10 is less than or equal to the average of 1 squared, 2 squared, 5 squared, 6 squared and 10 squared. Let A1, A2 up to A and B in R. Then the square of 1 over n times the sum of r equal 1 to n of ai is less than or equal to 1 over n times the sum of ai squared from I equal 1 up to n. Proof. The magic vectors we are going to use this time are x equals a1, a2 up to an and y with 1 over n in each component. First, we calculate the absolute value of the dot product. This is going to be the absolute value of the sum from I equals 1 up to n of ai over n. Of course, we can pull out the constant scaling 1 over n. As for the product of the norms, we have the product of the square root of the sum of the squared ai's, with the square root of the sum of 1 over n squared from I equal 1 to n. But adding 1 over n squared n times is just n times 1 over n squared, or 1 over n. This gives us 1 over the square root of n. By Cauchy-Schwarz, the absolute value of the dot product is less than or equal to the product of the norms. Since we have non-negative terms, we can square both sides. Therefore, the square of the average is less than or equal to the average of the squares. The final example doesn't have a cute saying, or at least I can't think of one, but the symmetry is pretty sweet. And just like in love, it is easier to see beauty than describe it.